it's good for. So the motivation basically is that it plays the role of the spinor bundle, but not for, in quantum theory, not for point particles, but for fermionic strings. And we want a generalization of this bundle. And the way Stolz and Teichner was thinking about this, and they also made up this word, stringor bundle, is that they think about it as a bundle of an infinite dimensional vector bundle on the free loop space of the manifold. And this bundle has a speciality that if one is at a loop gamma, and this loop gamma is like split into like two halves, so two paths emerging at the base point and meeting at like one half of the loop. So these paths are called beta 1 and beta 2 here. Then the fiber of this bundle on the loop space is supposed to be a bimodule over an algebra, over two algebras, and the algebras are coming from a bundle of algebras over the space of all paths. So this bundle has this complicated bimodule structure. In fact, the algebras are supposed to be von Neumann algebras. Right. And moreover, there is a very difficult thing, namely this confusion product. So once we are agreed that loops can be split into two halves, then there is this situation that one has now three paths connecting 2 points, and associated to these three paths are three loops. So one loop here on the left, one loop on the right, and one loop going all around. And Stolz and Teichner sort of saw, by analogy from other situations, that it would be good if this stringor bundle would have a property related to these three loops, namely that the fibers over this loop and this loop, the tensor product, give the fiber over the whole loop. And tensor product, because we're talking about bimodules over von Neumann algebras, tensor product is the confusion tensor product. Okay, that's what I wrote. There are in this paper, there are some ideas how to do this and lots of motivation. Why it's good to do this, but in the end there was no construction, neither of the bundle, nor of the algebras, nor of the confusion product. And finally, my student Peter Christel and I, we worked it out, so to say. I mean, it was still very complicated. We wrote 3 papers about this. And in the end, we also managed to construct this confusion product in a certain way. But I don't want to tell this story today, because I don't want to tell it today. Rather, today, what I want to do is I want to explain another construction of the stringor bundle, which finally leads to the same result, but has the advantage that it is sort of better understandable because it's completely analogous to the usual construction of the spinor bundle. That is, we are making these 3 steps. So first, take a group, the spin group in the spinor case, choose a representation, and then associate that representation to the frame bundle of the manifold. That's the usual construction of the spinor bundle. And what I want to explain today is that there is a completely analogous picture in this higher categorical world. I mean, we haven't seen higher categories yet, but the picture is so that the spin group is replaced by a categorical group, the string group, string 2 group. And then the main point of, or main part of this work is a construction of a representation of this 2 group. And since it's a 2 group, it's of course represented on a 2 vector space. And I will explain what exactly that is, and then I will briefly explain that there's a canonical procedure how to associate to 2 bundles representations of 2 groups to get 2 vector bundles. And that's how it's going to go. And this is joint work with Peter Christel still and Matthias Ludewig. Okay, so we start by saying what the string group is. There is this the first and sort of most famous version of the string group constructed by Bayes, Kranz, Schreiber, and Stevenson in 2005 also. And so I explained some details of this construction. It's not too relevant later. So they construct this two group as a crossed module. Okay, so crossed modules are these gadgets that are equivalent to actual two groups, but sort of easier to understand. In particular, when we talk about topological two groups or Lie two groups. So then a crossed module, what is it? It's just a group homomorphism between two groups, and then the range group has to act on the domain group in a certain way. That's it. And here these people, bias and so, they choose the following groups. So there is a Lie group involved, which finally for the string group will be the spin group, the ordinary spin group. And this group has this universal or basic central extension. And it was sort of clear from other contexts that in somehow the central extension is involved into this string theoretic considerations. So in that perspective, this is a very natural thing to do. So we have this central extension, and the other group is chosen to be the path in the group G starting at the identity element. So now the homomorphism itself is very easy to say what it is. From the central extension, we project down to the based loop group of G, and then we include just loops into path. So this is very simple. However, the action that we have to define, so we need an action of the path on the central extension, that was very difficult to define, and it is complicated. It's done in a Lie algebraic way, and finally integrating up this action to a group action. So it's certainly complicated. So the first detail I want to explain today is that there is a simplification of this model in which this difficult action becomes completely canonical. So this is a very recent work of Matthias and me. So we have these papers out, but now have to improve them because later we notice the simplification. So the simplification is in fact very simple. The idea is very simple. Just make these groups slightly smaller. For example, instead of all paths starting at the identity element, we just take the flat path. This means that the derivatives vanish at the endpoint. I'll explain in a second why this is good. So this is also a Frechet manifold. And for the central extension, we restrict the central extension to those loops that are only supported on one half of the loop. So the base loops are just constantly equal to the identity on the other half. So it's a slightly smaller thing. Then the homomorphism, it's defined as before, but the action now becomes simple and canonical. And I claim this, let me prove it, that it's simple and canonical. It's just this formula. So because we used flat paths, we can take a path, beta, and form a trivial loop from it by just going back and forth. Beta is a path, so it go back and forth. This makes a loop. This is this loop, beta, cup, beta. Okay, so then it's a smooth loop again because of this flatness condition. So the tilde means that we lift this loop in some way to the central extension and then just conjugate. Because it's conjugation and the extension is central, it doesn't matter how we lift it, and that's it. There is no additional structure, nothing needed on this. All right, so there is just one subtlety. To have a crossed module, there is this so-called Pfeiffer identity which has to be satisfied. The Pfeiffer identity is telling you what happens when you act with something that's in the image of this group. Then it's like an action of the group on itself. It has to be the conjugation action. And this is not automatically satisfied. It's only satisfied because of our second simplification, namely that we have here this restriction to loops supported on the first half, and because the central extension has a property that we call disjoint commutative. So disjoint commutative for a central extension of a loop group means that if you have elements in the central extension that project to loops, and these two loops have support on disjoint intervals, then the elements in the central extension commute. So this is something that makes sense for all central extensions of loop groups. It hasn't been sort of appeared that much in the literature, although it's certainly known that many loop group extensions have this property. For example, it appears when you consider these nets of observables, of observable algebras. Then, for example, there's this book of Fröhlich and Gabbiani where this property appears. It just doesn't have this name. However, Matthias and I prove that central extensions of simply connected semi-simple groups, or of loop groups of simply connected semi-simple groups, are always disjoint commutative. So this construction just works, and this gives one of these crossed modules, or Frechet-Lie 2 groups. So let me summarize this. So what we get is this crossed module that we call the string group, and it sits in a two-group extension, so it projects to the classical spin group. I can also show how that works. Oops. So here's like the cross-module picture. Here's this cross-module that we just constructed. The spin group is an ordinary group, so it corresponds to the trivial cross-module, just the identity map and conjugation action. And here BU1 corresponds to the trivial map to the point. It's a delooping of U1 as a crossed module. And our string 2 group fits into this extension, and it's a central extension of two groups in a certain way. All right, and also there is classification theory for such two groups made up by Bias and Lauda and Chris Schomer-Priest. So in general, such a two-group extension of an ordinary group by BU1 will have so-called K-invariant, which lives in the smooth group cohomology of that group with values in that group, which in our case is just H4 of B spin, which is Z, and the K-invariant of the string group is just the generator of this Z. Okay, so it's this shows that it's a correct two-group. All right, so are there any questions at this point? All right, so now we have this two-group sort of made up in some way from loops and paths and ordinary groups. And so this is around for, as I said here, 2005, so it's almost 20 years. And constructing a representation of this string group has really been an open problem for all this time, and it's very difficult. And I'm very happy that we have been able to solve it. And I will explain it now, how we construct a representation of this two group. So now one of the most important parameters that one has when constructing two-group extension is to choose a good model on what the representation is. What is a two-vector space? And there are many proposals, right? Kapranov-Wowodzki, two-vector spaces, Weiss-Kranz, two-vector spaces. One can just take abelian linear categories like in the TQFT world. And this is all sort of nice, but too unrelated to this geometrical intuition that we have in the string group. So what we finally choose are Schreiber two-vector spaces, because I think Urs was the first using this picture. So this is just, so the picture is just so that a two-vector space, a single two-vector space, is just an algebra, just an ordinary algebra. The important thing is to consider the right morphisms, bimodules, of course. We know this by now. There are many flavors of what algebras to take, so right now I'm just generically talking about algebras. I think about unital, associative, and maybe finite dimensional algebras in the first place. Later we have more sophisticated types of algebras. So I wanted to make such a table with analogies. So for example, so on the left there is a classical algebra with classical vector spaces, and on the right there are two vector spaces. So because the morphisms are bimodules, this means that the isomorphisms are invertible bimodules, which means that the relation of being isomorphic is exactly the relation of being Morita equivalent for algebras. So now we want to construct representations, so we should care about the general linear group of a two-vector space. And in the first place, it's just the monoidal category of invertible A bimodules, when A is our algebra. Right? Then the general linear group consists of the invertible bimodules. However, we have to have in mind that later we want to make an associated bundle construction. And for that, we need representations to be continuous, because otherwise the resulting bundle will not be continuous or locally trivial. So what we need is a smooth or at least continuous model for the general linear group. And well, just the category of bimodules, there is sort of no topology on all bimodules or something. So we make it sort of smaller. We have to make it a little bit smaller to give it a topology. And the solution is to consider the so-called automorphism 2 group of the algebra A. So that's again here given as a crossed module. So the first group is the group of units in A. The second group is the group of automorphisms of the algebra. And this homomorphism is just associating inner automorphisms to units. And the action of the automorphism group on the units is just the action as automorphisms evaluation, if you want. So this is the automorphism 2 group of an algebra. And this is, if A, for example, is finite dimensional, then this is a Lie 2 group. So they are all Lie groups and everything is smooth. Okay, so that's fine. So now I made this isomorphism symbol here, but you may have noticed that that's not quite true, because an isomorphism here would mean that every invertible bimodule is sort of corresponds to an automorphism, right? So if you have an automorphism of the algebra, let's say, let's make some space. Say phi is an automorphism of the algebra. Then there is a corresponding invertible bimodule, often denoted by A phi, where you just twist one of the actions, say the right action, by this automorphism. So this is an invertible bimodule. Now the question is, are all the invertible bimodules of this form? And that's in general not true. Then the algebras for which this is true are called Picard surjective. So this isomorphism doesn't hold for all the algebras, but what is true is that every algebra can be replaced by a Morita equivalent one, which is Picard surjective. And Morita equivalence is isomorphism, so this is acceptable. We can go to an isomorphic two-vector space and then model its general linear group by a Lie 2 group. Okay, so that's what our representation will go into this Lie 2 group, and then finally it will be continuous. Right? So that's the idea what a representation is. A two-group homomorphism from a general 2 group, here it's called gamma, so later it will be string, to this automorphism 2 group. So before continuing, we have to, unfortunately, we have to leave the setting of finite dimensional algebras. I mean, the string 2 group was already Fréchet and infinite dimensional, so we cannot expect that we land in some finite dimensional algebra, so we have to go to infinite dimensions. And here are some more analogies that, yeah, so the justification is sort of poor, I would say, but that's how we think about it. So what's an inner product? What's the 2 equivalent of an inner product space? We think it should be a C-star algebra. Okay, and then if we have an inner product, we want to improve the general linear group to a unitary group, because we construct unitary representations, of course. That's very easy. We just replace the units of the algebra by unitaries and the automorphisms by star automorphisms. Then, of course, star automorphisms act on the unitaries. And this is then like a C-star version of the automorphism 2 group of an algebra. Of course, when A is a C-star algebra, we have to talk about topologies here. There is no smooth structure, but there are topologies one has to care about. This I will explain it probably later or probably not, but this can be sort of treated. So a unitary representation is then 2-group homomorphism to this unitary automorphism group. And so finally, so what's a Hilbert space? So if an inner product space is a C-star algebra, then the idea is that to get a Hilbert space, we have to complete, well, and C-star algebras complete to von Neumann algebras. So that's why this analogy works quite well. And that's where we will end up in the end with a von Neumann algebra and its unitary two-group. All right, any questions at this point? Yeah.
What is then the analog of Morita?
Yeah, that's a good question. The full bicategory needs according modifications. Yes, so for example, for the C-star algebras, you would take Hilbert C-star bimodules, and for von Neumann algebras, that's a good news. For von Neumann algebras, it's again simpler. There, it's just bimodules again.
Mm-hmm. Mm-hmm.
Yeah.
Okay.
Does that answer the question?
Yeah, and then you have also a similar justification that you can use the small out instead of the big bimod, or because you said it's not Picard something?
Yeah, that's a very good question. No, we don't have justification for this. In general, for general C-star algebras or even general von Neumann algebras, this isomorphism will not persist, not even under Morita equivalence, I believe, at least, unless some special situations are given. The point is that our representation will end in this sort of smaller unitary group. So we don't care if there are more representations. Yeah.
Makes sense, thanks.
Also, I should mention that there are many ways of weaken all this definition. For example, I could allow weak two-group homomorphisms like these butterflies or things, but for us it's not necessary. Everything is completely strict here. Okay, then I'll go on and construct the representation. So what we want is this two-group homomorphism from string D to this unitary automorphism group of some algebra. We don't know yet what A is, but we'll see. And so in the details, it looks like this. So this is the cross module for the string group, and this is the cross module for the unitary group of the algebra A. So we need to construct maps here and here, such that this diagram is commutative, and such that the actions, so remember that this acts here and this acts here, they have to be exchanged under these maps. All right, so here's how the lower map is constructed. So now this is, we consider this Hilbert space of spinors on the circle with artificial d dimensions added. So the motivation to do this is that sort of Stolz and Teichner proposed that that's the right thing to look at, and we did look at it, and it worked. That's the motivation. Well, otherwise, I mean, the string group consists of these loop theoretic things, so that there is some loops involved is not surprising here. So we need this Hilbert space, and it has, okay, we will see. So this is a Hilbert space, it's a real Hilbert space, and real Hilbert spaces have Clifford C-star algebras. So we take this Clifford, it's basically defined as in the finite dimensional setting by a universal property, then you complete. Okay, so now this Clifford algebra has this universal property, and as always, when I have an orthogonal transformation, or an orthogonal transformation of the vector space, the universal property will produce a corresponding automorphism of the Clifford algebra. This is just like in finite dimensions, just that in infinite dimensions it has this fancy name, it's called the Bogoliubov automorphism, but it's just induced by the universal property. So there is this morphism from the orthogonal group of V to the automorphism, the star automorphism group of this Clifford algebra. And then, so how are we getting, so we need to involve loops in the group G in some way, right? So how do we do this? So this is simple. So if I have a loop of orthogonal transformations, then I can act pointwise on this CD factor. So this is also a loop. It has a CD component, the elements of V. So this gives me an orthogonal transformation. So the loop group embeds into this orthogonal group. Oh, by the way, these are Banach-Lie groups, actually. This is a Frechet-Lie group, so this is still sort of smooth in the sense. So now the problem is that we need to map from here, and there are no loops, there are just paths. And so now there are again many options, but we think about these paths as being half of a loop. And so we have to go from full loops to half of the loop, and the idea is to take half of the vector space. So we replace V by a smaller vector space, namely the space of spinors on the circle, only supported on the one half of the loop. So this sounds familiar now. And we take the corresponding Clifford algebra, denote this by A. So this will not be quite the final answer, but it's an approximation to what the algebra, the two vector space is on which we represent. It's this Clifford algebra of half spinors on the circle. And once we've done this, we obtain this lower line here. So this is just the same as before, just for this smaller vector space. But now, because now it's much more natural to come with the paths acting as orthogonal transformations, because the spinors are only supported on one half, and I act pointwise with the path of orthogonal transformation on this one half. And then finally, we just project from spin to the orthogonal group here pointwise. And this is exactly our lower line. It's exactly what we want here. Okay, so that's one part of our representation. For the upper line we need here, let me do some preparation. So there is this classical representation theory of operator algebras due to Araki and Presley-Siegel mostly. So this vector space, the Hilbert space V that we considered, has a Lagrangian subspace, the APS Lagrangian. It's basically you take the Dirac operator on these spinors on the circle and take the positive modes. Like the spectrum will be Z. Yeah, there is a slightly subtlety. We take the odd spin structure on the circle. This means that the spectrum will be half integers. And then we can just split it at 0 and get like an equal distribution into positive and negative modes. Just take the positive ones, and then it's a Lagrangian subspace. So this subspace is only used for this only thing, namely if one has this Lagrangian, one can form the Fock space on which the Clifford algebra acts by creation and annihilation operators in the usual way. It's just like in finite dimensions. All right, so we use this Fock space. And now there is this very classical piece of operator theory. So when we consider now the bounded operators on this Fock space with U, with the following property, namely that they implement Bogoliubov automorphisms in that way. So there need to exist an element G of the orthogonal group such that the Bogoliubov automorphism associated to G is conjugation by U. So this sort of looks tricky, but it is a very classical thing that people have done. And then we arrange all these operators for which there exist G's in a group, the group of implementers. And it turns out that not all orthogonal group elements have implementers, only some of them, and they form a subgroup, the restricted orthogonal group. And these are again Banach-Lie groups, and in fact this is a central extension by U1. And now we want to construct this string group representation, and now we relate this to the former central extension of the loop group. In this way, we know already that the loops map into this orthogonal group. One can prove that they land in the subgroup, in the restricted orthogonal group. So we can pull back this central extension of implementers to the loop group. And this is just a model for this basic central extension we considered earlier. So we have a commutative diagram of central extension in that way. And remember that we have this needs an action. Well, this needs to go into this unitary group of the algebra A. So it has to act somehow here. And now this is the basic idea how to. So this is this positive energy representation one usually has. Okay, but it's not enough. What we want is the following. So first of all, we don't want to land in these bounded operators. We also don't want to land in the Clifford algebra, and also not in A. So remember that A is the Clifford algebra of half of the thing, so it's a subalgebra. We want to end in the unitary elements of this. And so we need to factor this positive energy representation through the unitary elements of this algebra A. And also, we just want this lift for these restricted central extensions. So we need this map here. But unfortunately, this doesn't exist. That's just demanded too much that the positive energy representation factors through these unitaries. A is too small to do this. And now it's a point where we are forced to do this completion to 2 Hilbert space. We complete to a von Neumann algebra. So we complete in this representation on Fock space. So first of all, the Clifford algebra can be completed, but if one does this, one gets all of the bounded operators. So this Clifford algebra is a type 1 factor. The completion of this half Clifford algebra is a type 3 factor. And that's our von Neumann algebra N. That will be the final answer to this thing. And then here is the theorem that we prove. So first of all, this factorization from the last slide into the unitaries exists now. So that's the map here. So it goes to the unitary operators. And this diagram is commutative. So this is basically a matter of definitions. What is more complicated is that it's really a 2-group homomorphism. For this, one needs to check that these actions are respected. So the action on the left was this very canonical action that I just explained. You double, lift, and conjugate. And on the right-hand side, this action can be, so that's how we prove it. This action can be written using a gadget from Tomita-Takesaki theory for this type 3 factor, namely Hagerup's canonical implementation. And then we prove sort of that this doubling and lifting here corresponds to the canonical implementation here. And that way we show that these actions are exchanged. So this is difficult and complicated. So maybe that was the point where the thing was stuck before. So in the end, we get this 2-group homomorphism as desired to the unitary group of this von Neumann algebra 2-group. And then, we also show that this representation is continuous. So the string 2-group is a Frechet thing, but these von Neumann algebras, they don't have Frechet structures. They just have topologies. And in fact, very intriguous topologies. For example, this automorphism group is equipped with the so-called Hagerup's U topology. It's precisely that topology that does the job. We have searched for a longer time for appropriate topologies, but this one did it. It's sort of the topology on the automorphism group that comes near as possible to allow something like an exponential law that if you have a map into this automorphism group, that this is the same as like a parameter, like this, okay? It's not quite true, but it's almost true. And there is no topology on the automorphism group that makes these two things really correspond bijectively to each other. So that was kind of the problems we had to face here. Any more questions at this point? All right, then I go on. So now I want to explain the stringor bundle. And so if a 2-vector space is an algebra, so what's a 2-vector bundle? Is it an algebra bundle? That would be too simple. So for example, algebra bundles up to Morita equivalence are classified, this Donovan-Karoubi result, classified by here's something that gives the Morita equivalence class of the complex algebra. And then there's this annoying torsion thing that tells us that that can't be the right thing because we want to get rid of this torsion. Also, there is no gluing property that such algebra bundles have along bimodule bundles. So what we do is we have to stackify this. So if you want using the plus construction, for example, described by Christoph Schweigert and Thomas Nikolaus for 2 stacks, and it goes like this. So we have local algebra bundles, and on the overlaps of open sets, in the simplest case, we have invertible bimodule bundles for the restrictions of the algebra to these open sets. And then on the triple intersections, such coherence condition, and another one on the fourfold intersections and so on. Let me skip these details. So this is our notion of two-vector bundle, and it's in fact very nice because ordinary algebra bundles are examples, right? They're global algebra bundles. I just restrict them, and then the bimodule becomes trivial. But also bundle gerbs are two-vector bundles. For them, the algebra is trivial, but just the bimodules are just line bundles. And, okay, that's very nice. So by definition or by construction, they form a two-stack, and the classification is resolved. So the torsion factor is gone away if one restricts to the invertible two-vector bundle. So they have a monoidal structure. Okay, so all two-vector bundles will, of course, not classified by this. For this one needs a version of elliptic cohomology that's not clear yet what exactly that is. All right, that's at least the the expectation. So now I want to go briefly through this associating process. So the message is simply, if one has a two bundle for this unitary group of von Neumann algebra, so this just means, so if you know about this, think about non-abelian bundle gerbs. So it has no information on the open sets, but on the intersections it has like bundles for these two groups, which just means that it's an ordinary principal bundle for the unitary group with an anchor map. Okay, and this anchor map provides a tensor product for such bundles, and then we can like form the usual compatibility condition. So this is a two bundle for this unitary automorphism group, and if one has this, so the classical situation would be you have a GLN principal bundle, and now I say how to form the vector bundle using the defining representation. Okay, so the two vector bundle associated to this looks like this. So I put the trivial, say, von Neumann algebra bundle. So let's immediately be in the von Neumann case here. So it takes a trivial von Neumann algebra bundle. Then to this principal bundle, we associate the von Neumann algebra and use this anchor to twist the left action, right? If you associate and you have a bimodule, it's clear that the right action is unproblematic, but the left action doesn't work without doing anything because it's already used here in this association process. But these principal bundles here are made exactly so that these anchor maps resolve this problem. By twisting the left action, we get a bimodule bundle over the double intersections. And then we prove this important key lemma, which is also complicated, that this tensor product using the anchor thing goes directly to the confusion tensor product, fiber-wise confusion of these bimodule bundles. And so this isomorphism becomes this isomorphism, and then we have a two-vector bundle. Now the idea is if we have a principal bundle for some general crossed module gamma, and we have a representation, then there is a way to push bundles along their structure groups, along homomorphisms, and then we do what we just explained for this pushed bundle, and then we get a two-vector bundle from a principal bundle and a representation. So summarizing, that's how we define the stringor bundle. So we take the string two group, takes this representation on this von Neumann algebra, and associate. So this is our definition of the stringor bundle. All right, so let me come to some conclusions. So first of all, there is this slogan that higher structure transgresses, higher structure over manifold, transgresses to lower or ordinary structure on the loop space. And while transgressing, it picks up additional features. For example, it picks up compatibility with this loop fusion that I explained earlier. And it also picks up some compatibility with thin homotopies between loops, right? Loops are thin homotopic if they are homotopic via a rank 1 map. And for example, if you take, so the easiest thing to think about, a bundle gerb over the manifold, and you transgress it to the loop space, you get a line bundle. This is this very famous Brzezinski-Gavetski construction that was used in conformal field theory to transfer like one notion of B field, connection on a bundle gerb, to another notion of B field, line bundle on the loop space. And it picks up exactly one of these fusion products and an equivariant structure with respect to thin homotopy. So this line bundle, so the fibers, if you have two thin homotopic loops, then the fibers of this line bundle are related by a given isomorphism. So that's this thin homotopy equivariant structure. And although at current stage we don't have a general transgression procedure for two vector bundles or two Hilbert space bundles, we can sort of see that such a procedure, so we can write it down in case of the stringor bundle. And if we do this and perform it, then we get exactly Stolz-Teichner's loop space bundle together with its confusion product. So remember that my student Peter Christel and I constructed this confusion product on the loop space separately. And then we had this the story that I just explained. And then we can prove as a theorem that these two confusion products coincide on the loop space. So by this we believe that everything is consistent and correct. Right. Okay, so this is like a justification for like both like our construction and Stolz-Teichner's original construction, which where the setting is sort of unclear and it's not clear where this fusion product comes from, but now we explain it sort of by saying, well, it has this fusion product because it's a transgression of a two-vector bundle to the loop space. Another application of this stringor bundle is in functorial field theory. So finally, I also come to some Cobordisms now. So we propose that the stringor bundle is the value of a smooth functorial field theory on the point. So smooth, by smooth I mean in particular, or maybe it's not the right, I should have said over M or something, right? So I think about that. So it's a two-dimensional theory, so let's think about some Bordism, some two-dimensional. And so by smooth we mean that all the Bordisms are equipped with a smooth map to a target space. So this is not a quantum theory, it's a classical field theory where the target space is still involved. But this smooth map can be regarded as geometric structure on the Bordisms, for example, in the sense that Dimitri and Daniel describe in their papers. Okay, and so this means that the point, an object in this bi-category, is not just a point, it's a point with a map to M. So this means that there is a manifold of points, namely M. M is the thing on the point. And so it makes sense to say that on the point we have the stringor bundle over M. So what are some implications of this proposal? So we know from, sort of intuition and other examples of such smooth functorial field theories that the transgression of the thing you put on the point is the value on the circle. So this means that Stolz-Teichner's loop space bundle, which we identified as the transgression of this stringor bundle, is the value on the circle. So this is like the state space of fermionic string theory on the circle. And the confusion product is then exactly what it assigns to such pair of pans, right? Two circles come in, one circle comes out, that's the confusion product. So there is this conjecture that we have, and we haven't endeavored to check it really, because in principle one should now be able to compute the value on the point, on the torus of this field theory, right? Because it's determined from the value on the point, so it knows what the value on the torus is. So in some way there must be some way to compute it, but we haven't managed to do it. But if there is a way, there is a check one can do, a deterministic check if it's correct, because we know what this fermionic string theory does on the torus. Namely, there is this the string structure that enters the construction of the stringor bundle by a result of Bunke. It cancels this anomaly that fermionic string theory has and makes the value on the torus a well-defined function. And in principle, it should be possible to check that we get this function. Okay, but there is more work to do. For example, we would need like connection on a stringor bundle and then an induced connection here and so on. It's not clear at all what that means. There are many open questions that have to be attacked. So I wanted to explain some more things. Yeah, so in principle, we could now consider twisted stringor bundles. Maybe that's not so interesting. So this is more interesting. Yeah, we would like to put a connection on the covariant derivative on the stringor bundle. That would be one step to make this transgression business clearer. And then there are even more open questions that are, of course, very interesting, but maybe I'm not sure if doable, right? Once we have this connection on the stringor bundle, then of course one would like to try to define a Dirac operator on the section. So neither it's clear what kind of operator it is, nor it is clear what sections exactly are. And then even more speculative, we want to compute the index, supposed to compute the Witten genus. That's a conjecture of Stolz and Teichner. And also there's the Stolz conjecture that says that it must be related in some way to positive Ricci curvature on the manifold. But it's okay, that's just for homework for you. All right, so thank you very much.
Questions for Konrad? So I have a question just kind of broadly about the geometric structures on the bordisms that you have. So I suppose the connection would be necessary to say what happens on the bigger bordisms. But on the circles, you expect spin structures to show up. So there should be two circles, one for the bounding spin structure, one for the non-bounding. In the construction, if I understood correctly, you use the bounding spin structure on the circle to define all these modules. Is there an analogous one for the non-bounding?
So in this field theory, the geometric structure consists of maps to target space and spin structures, as you say. So it's correct that there are two circles.
Probably conformal structures or something as well, I think. Yeah. It's certainly not topological, because the value in the circle is not finite dimensional.
No, I think it's mapped to target space and spin structures. That's.
We can discuss more later, but if that's the case, if it's only that structure, then the value in the circle has to be a finite dimensional vector space, which it seems like it's not.
Why does it? I mean, there is
generalizability for TFTs and families.
But it's not TQFTs. We have mapped to the target space, so there is non-trivial geometry on the bordisms. It's not a TQFT. The argument doesn't work.
So does the bordism have any geometry, or is it just a topological bordism with a
smooth map to the target space?
So there's no metric, that was what I'm getting at.
No, there's no metric. I mean, not necessarily. I mean, one could, right. I mean, at some point, of course, you want to add metrics to get kinetic terms for the strings. So here we just sort of treat this topological and anomalous part of the fermionic string, right?
So the free fermion definitely needs a del bar operator to do things like take polarizations that you mentioned. So if that doesn't exist, maybe we should talk about it afterwards, but
okay.
I'm confused about something.
Okay, so but you're right, there are two versions of the circle in this setting, and they both get assigned to things. But this former choice of odd spin structure is something different, right? So this hits like very far in the details and the construction of this algebra and representation. It's not the circle; it's another circle than we have in the bordism side.
Okay, Alexander.
Thank you. Maybe a super stupid question. So you say this technology is there for defining like the action functional of these fermionic strings. And then this technology uses stuff like von Neumann algebras, which is typically associated to quantum stuff. So is there some way to understand why you need these kind of sophisticated functional analytical things?
Well, we do have quantum, right? Because when I say the value on the torus, then we mean that the fermions have been quantized, right? We do the fermionic path integral. That's a quantity that we want to compare and can compare.
Okay, so it's not just the integrand, but it is like...
It is a bosonic integrand, but the fermions are already integrated out. That's where this anomaly sits in, right? The integral for the fermion, for the fermionic part, that's anomalous, that we cancel and integrate.
Okay,
At this
so
point
there-
already you need Hilbert spaces and things like
Okay,
that.
so there already happened some quantum
Yes.
stuff which is integrated out, and then you still see the shadows of von Neumann algebras in the game somehow.
Yes.
Yeah, thank you.
Otherwise, I mean, it's a good question, and we have also struggled a lot with. We have tried for a long time to stay in the setting of C-star algebras because we didn't know anything about von Neumann algebras. We had to learn all this. We didn't want to. We didn't ask for it.
Nobody wants to learn that. Yeah.
But at this one point where we constructed this representation, there was no way to proceed with C-star algebras. Whereas this technology of von Neumann algebras immediately sort of did the right thing.
Interesting.
Any other questions? Not. Let's thank Konrad again for the
Thank you.
very nice talk.